Before Feynman broke physics, there was already a crack in the foundation. It appeared in the 1600s. A mathematician named Fermat noticed something uncomfortable about light. When light travels through air and then enters water, it bends. You've seen this. A straw in a glass looks broken at the surface. The light coming from the straw doesn't travel in a straight line from the straw to your eye. It kinks at the boundary. Why? The standard answer is Snell's law. Light bends according to a specific angle that depends on the materials. Clean, geometric, predictable. But Fermat asked a different question. He asked, why that angle? And he discovered something unsettling. Light doesn't take the shortest distance. It takes the shortest time. The path light actually follows, the kinked one, gets the photon from the straw to your eye faster than the straight line would. Because light travels slower in water than in air, the bent path compensates. It spends less distance in the slow medium, more distance in the fast one. Light, somehow, is optimizing. But optimizing requires knowing the options. You can't choose the fastest route unless you've compared it to the alternatives. A photon leaving the straw would need to know where your eye is. It would need to know the speeds in both materials. It would need to calculate which angle minimizes travel time. And then it would need to choose. This is called the principle of least time. It works. It predicts the bending of light perfectly. Physicists still teach it, but it implies something deeply wrong. A photon doesn't have a brain. It doesn't have a map. It doesn't plan. So how does it know? For centuries, physicists shrugged. They treated the principle of least time as a mathematical curiosity, a shortcut for calculation. Not a description of reality, but it is reality. The photon genuinely does take the fastest path. Every single time. Feynman didn't solve this problem. He made it worse. He proved that the photon doesn't know which path is fastest, because it never chooses at all. You've probably heard of the double-slit experiment. Two narrow slits cut into a barrier. You shine light through them. On the screen behind, you don't see two bright lines. You see many, alternating bands of light and dark. An interference pattern. The explanation you were given: light is a wave. Waves from both slits overlap. Where peaks meet peaks, brightness. Where peaks meet troughs, darkness. Simple. Intuitive. Wrong. Here's why. Turn down the intensity. Send one photon at a time. So dim that only a single particle of light exists in the apparatus at any moment. Now there's nothing to interfere with. One photon, one particle. It has to go through one slit or the other. Fire enough of them, one by one, and watch where they land. The interference pattern still appears. One photon at a time. No other photons present. And yet, somehow, interference. You might try to rescue the situation. Maybe the photon goes through one slit, but it's still a wave, and it somehow interferes with itself. Fine. Test that. Put detectors at the slits. Watch which slit each photon goes through. The moment you do this, the interference pattern vanishes. Now you get to bright bands, one behind each slit. Exactly what you'd expect if photons were little bullets passing through one slit or the other. The act of checking, just checking, not blocking, not disturbing, destroys the interference. This is not a matter of experimental clumsiness. This is not about disturbing the photon. This is what happens. Measurement changes the outcome. Not because you bumped into anything, but because reality itself is doing something different when you're not looking. The photon, when unobserved, does not go through the left slit. It does not go through the right slit. It does not split in half. Something else is happening. Something that doesn't fit into the categories of particle or wave or any other model you've inherited from experience. The photon is not traveling through space the way you think things travel. And if you try to catch it in the act, if you try to see which path it took, it stops doing whatever it was doing and collapses into behaving like the classical particle you expected. The two-slit experiment is not about slits. It's about the fact that the question, which path did the photon take, doesn't have an answer. Not because we don't know, because the question is malformed. In the 1940s, Feynman was trying to rebuild quantum mechanics from scratch. Not because the existing version was wrong. It worked. It predicted everything correctly. But it was ugly. A patchwork of rules, wave functions, probability amplitudes, operators, collapsing states. It felt like a language translated too many times. Feynman wanted to know what reality was doing underneath all that math. And he found something. He found that you could throw out wave functions entirely. You could throw out the Schrödinger equation. You could describe everything with a single idea. A photon traveling from point A to point B doesn't take one path. It takes all paths. Not metaphorically. Not probabilistically, in the sense of we don't know which one, so we average them. Actually all paths. The path that goes straight. The path that veers left, then right, then left again. The path that loops around the room 5 times. The path that exits the universe and comes back. The path that spells your name in cursive. Every geometrically possible path between A and B is taken simultaneously. Each path contributes a number. Feynman called it a probability amplitude, a complex number with a magnitude and a phase. The phase is what matters. It's like a clock hand. Each path has a clock, and the clock ticks as the photon travels along that path. When the photon arrives at point B, you add up all the clocks from all the paths. Most of them cancel out. A clock pointing up, a clock pointing down. They annihilate each other. This is destructive interference, but some clocks certain paths stick at nearly the same rate. Their clock hands point in almost the same direction. These paths don't cancel. They add. This is constructive interference. And the paths that contribute most, the ones where nearby paths have almost identical clock readings. The ones where the time taken is stationary, where a small detour doesn't change the clock much. The ones that extremize travel time. The paths Fermat already knew about. But here's the thing. Fermat thought light chose the fastest path. Feynman showed that light doesn't choose anything. The straight line, the classical path. The one you see is not selected by the photon. It's the statistical residue of a quantum interference process involving every possible path. You're not seeing the path the photon took. You're seeing the only path that survived the cancellation. This is the part that destroys your intuition completely. You look at a laser beam. It's straight, perfectly straight. You're not hallucinating. That straightness is real, measurable, repeatable. But the photon didn't travel in a straight line. So why does it look like it did? Because of destructive interference. Imagine every possible path the photon could take from the laser to the wall. Infinite paths. Each one contributes a little rotating clock hand a phase. Now think about the straight path, and think about a path that's almost straight, one that deviates just slightly, curves out a tiny bit and comes back. These two paths take almost the same amount of time. Their clocks tick almost in sync. Their phases are nearly identical. So when you add them together, they don't cancel. They reinforce. Now think about a path that veers wildly off to the side, swoops up to the ceiling, curves around, comes back down. This path takes much longer. Its clock has ticked way ahead. Its phase is completely different. Compare it to a nearby path, one that also veers off, but slightly less. That path also takes longer, but not quite as long. Its clock is in a different position. Add these two together, and they cancel. In fact, every extreme path anything far from the straight line has neighbors with wildly different phases. They all cancel each other out. The only region where paths don't cancel is near the classical path, the straight line, because there, all the nearby paths take about the same time. Their phases align. They add up. This is why you see a straight line. Not because the photon chose it, but because every other possibility destroyed itself. The straight line isn't privileged. It's not special. It's not the real path. It's just the only path whose neighbors didn't annihilate it. You can test this. Block some of the paths. Put obstacles in the way. Force the photon to take more extreme routes. Now, extreme paths can't cancel each other out anymore, because some of them are missing, and suddenly, the photon starts appearing in places it shouldn't. The interference pattern changes. Light bends around corners, diffracts. This is not light squeezing through gaps like a wave on water. This is reality recalculating which paths survive the cancellation process. When you change the available paths, you change which clocks add up. A straight line is a conspiracy, a fragile agreement between infinite possibilities that just happens to hold under normal circumstances. But it was never the truth. It was always an approximation. You were taught that. Mirrors work because of the law of reflection. Angle of incidence equals angle of reflection. Draw a perpendicular to the surface. Measure the angle coming in. The light bounces off at the same angle going out. Clean. Geometric. Obviously true. Except it's not what's happening. A photon hitting a mirror doesn't bounce. It takes every possible path from the source to your eye that touches the mirror somewhere. Any point on the mirror, every point, the photon leaves the source. It could hit the mirror at the center. It could hit near the edge. It could hit anywhere, from each point on the mirror. It continues to your eye. Each of these path source to mirror point to eye contributes a phase, a little clock. Most of these paths cancel out. A path that hits far to the left has a very different length than a path that hits far to the right. Different lengths mean different travel times, different phases, cancellation, but there's one point on the mirror where something special happens, the point where the angle of incidence equals the angle of reflection. At that point, all the nearby paths take almost the same amount of time. A path slightly to the left takes almost as long as a path slightly to the right. Their clocks are nearly synchronized. So they add. That's why you see a reflection at that angle. Not because the photon bounced according to a rule, but because that's the only angle where the paths didn't cancel. Geometry is dead. The law of reflection is not a law. It's a consequence, a shadow cast by quantum interference. Lenses are worse. A lens bends light to a focus. You are told this happens because light slows down in glass. The center of the lens is thicker, so light there gets delayed. The edges are thinner, so light moves faster. This difference in speed compensates for the difference in distance. All the paths arrive at the focus at the same time. That explanation works, but it smuggles in the same problem Fermat had. It assumes light knows to synchronize its arrival. Feynman's picture is different. The photon takes every possible path from the source, through the lens, to the focus, paths through the center, paths through the edge, paths through every point in between. Paths through the center are shorter but slower. Paths through the edge are longer but faster. And by accident, pure geometric accident, all these paths take about the same time. Their clocks aligned. So they all add up. Constructive interference at the focus. Everywhere else, the clocks are out of sync. Cancellation. The lens doesn't bend light. The lens selects which paths survive. You can prove this. Block half the lens. Classical optics says you'll lose half the light. You do. But the focus is still there, same place, because the paths through the other half still synchronize. Now do something stranger. Cut tiny rings out of the lens. A Fresnel lens. Remove most of the glass. Leave only the zones where the paths are in phase. The focus remains sharp, clear. You've deleted most of the lens and it still works. Because the lens was never bending anything. It was always just a filter, allowing certain path combinations to survive the sum. Everything you thought was geometry, reflection, refraction. Focusing is interference in disguise. Here's the part that should bother you more than it probably will. In Feynman's path integral, the photon doesn't move through time. It doesn't start at point A, travel for a while, then arrive at point B. The formulation doesn't work that way. You give it to points A and B, a location and time for emission, a location and time for absorption. Then you sum over every possible path connecting them. But the sum doesn't care which point is earlier. You can reverse A and B. Swap the emission and absorption events. Run the calculation backward. The math doesn't change. The photon doesn't know which direction time is flowing. The probability amplitude for a photon to go from A to B is related to the amplitude for it to go from B to A by a simple symmetry. Time, in this picture, is just another dimension. The paths wiggle through. The photon doesn't experience duration. It doesn't travel from past to future. Both endpoints, emission and absorption, are given to the calculation at the start. The photon, if you can even call it that anymore, exists as a connection between those events, not as a thing moving from one to the other. This is why Wheeler and Feynman once considered an idea so disturbing it barely made it into textbooks. They asked, what if light doesn't propagate forward in time at all? What if every photon is actually a transaction between an emitter and an absorber, and the direction of time is irrelevant? A photon leaves the sun. 8 minutes later, it hits your eye. Or, your eye absorbs a photon. 8 minutes earlier, the sun emitted it. Both descriptions are equivalent in the path integral. The photon doesn't travel from the sun to you. It's a correlation between two events, the emission and the absorption. And the correlation is negotiated across all possible spacetime paths, forward and backward, until the sum converges on what looks, from your perspective, like a particle moving forward in time. You think causality is obvious. The sun emits, then you see, but the math doesn't need that order. It only needs the boundary conditions, the endpoints. This gets worse when you think about absorption. A photon is only real when it's emitted and absorbed. If there's no detector, no eye, no interaction at the other end, the the photon's existence becomes ambiguous. Some interpretations say the photon doesn't exist until it's measured. Others say it exists in superposition. Feynman's picture says, "Stop asking when it exists. It's not a thing that exists at moments in time. It's a relationship between moments." The path integral doesn't describe a photon moving. It describes reality stitching itself together across space and time, and the stitching happens to look like motion when you're trapped inside time, watching it one moment at a time. But you're not seeing what's actually there. You're seeing a projection, a shadow of something that doesn't travel. You might be thinking, fine, light is weird, photons are quantum, but this doesn't apply to real things. You're wrong. Feynman didn't develop the path integral just for light. He developed it for everything: electrons, quarks, atoms, molecules. Every particle that exists takes every possible path between emission and absorption. An electron in a wire doesn't flow through the wire. It takes every possible route through the wire, around the wire, briefly outside the wire, looping back, spiraling. The reason it looks like it flows through the wire is the same reason light looks straight. Destructive interference kills the extreme paths. Only the classical route, the one through the wire, survives the sum. But the electron didn't choose that route. It's just the only one that didn't cancel. You can test this with electrons too. Fire them one at a time at a double slit. They interfere with themselves, just like photons, because they're also taking every possible path. Now scale up. An atom doesn't have a definite position until it interacts with something. It's smeared across every possible location, weighted by the phase contributions of all the paths that lead there. A molecule, same thing. A virus, a grain of dust. Where does it stop? It does in single quotes T. The math doesn't have a cutoff. There's no place where quantum mechanics turns off and classical physics turns on. You are made of particles. Those particles are taking every possible path through spaceTime. Right now, the atoms in your hand are not definitively in your hand. There are paths where they're a millimeter to the left, paths where they're inside the table, paths where they briefly teleported to the other side of the room. The reason your hand looks solid, looks here, is because the overwhelming majority of those paths cancel out. The classical configuration, the one where your atoms are arranged in the shape of a hand, in the location you perceive, is the only arrangement that survives the sum, but the sum is still happening. You are not a collection of particles in definite places. You are a stable interference pattern. Feynman's path integral says that the entire universe is doing this. Every particle, every field, every event. Nothing travels, nothing chooses, nothing moves through time in the way you think. Everything is a sum over histories. The past is not a sequence of definite events leading to now. It's a superposition of every possible sequence, weighted by their quantum phases, most of which canceled out, leaving behind the single thread you call history. The future is the same. Not a garden of forking paths you'll choose between, but a quantum sum already being computed, and the choice you'll make is the one that survives the interference. This is not an interpretation. This is the math. This is what the equations say happens. Feynman found that you don't need particles. You don't need waves. You don't need collapse. You just need every possibility, all at once. And a rule for how they add up. And when you run that sum, the universe appears. Classical reality, the world of definite objects in definite places moving along definite paths, is not the ground floor. It's the pattern left over when infinity cancels itself out. You think you're watching things happen. You're not. You're inside the sum.